Welcome Math 347 fans to another video. This one we're going to be looking at first order differential equations that can be classified as linear. Similar to the last set of videos on separable differential equations, we'll see some classification and strategy, we'll see some exploration, and we'll see some applications, and we're going to do this in two chunks, having a look at classification and strategy in this first part, and having a look at applications of linear differential equations in the second part. Okay, so without further ado, an example that motivates the study of these linear differential equations. So let's have a look at this first order linear differential equation, and I'll tell you what makes a differential equation linear in a minute, but I think you'll agree with me that this differential equation is first order. It's in a little bit different form than what we've seen before, but I think if you stare at the left-hand side of the differential equation, you'll notice a couple of things, that there's a t squared and a 2t, so the derivative of t squared is 2t. And there's also an x and a dx dt, so there's a derivative of x, which is dx dt. That's to say that the left-hand side looks like the product rule. Okay, so t squared dx dt plus 2tx is the same as writing the first times the derivative of the second plus the derivative of the first times the second, where here the first function is t squared and the second function is dx dt. Okay, so we know all about the product rule. We know that the first times the derivative of the second plus the derivative of the first times the second is just the derivative of the product. So in this case, that's tx squared. So we can write the derivative of the product equal to t to the fifth, and if the derivative of something is equal to t to the fifth, we can integrate both sides here to come up with that something had better be 1/6 t to the sixth plus a constant, which allows us to solve quickly for x of t, 1/6 t to the fourth, plus that constant of integration over c over t squared. Now this should look very familiar to us. This looks like a one-parameter family of solutions, and indeed it is the one-parameter family of solutions to this differential equation. So questions you might be asking are the following: is this sort of magic always possible? And the answer is sometimes. You might be asking under what conditions this sort of magic is possible, and it turns out that this magic is possible when you have first order linear differential equations. And you might also be asking how you do it, and the way you do it is with something special called the integrating factor. Okay, so more on all of those things. What makes a differential equation first order linear, what is integrating factor, and also how to use it is just coming up next. Okay, so here is the definition of linear. A first order differential equation is called linear if it has the form a1 of t times dx dt plus a naught of t times x equals g of t. So we agree here that this differential equation is first order, right? A differential equation is an equation involving one or more derivatives of some unknown function. In this case, that unknown function is x, and we see its first derivative. The new wrinkle here is linear. By linear, we mean linear in the dependent variable and its derivatives, which in this case is x. So the only thing that's allowed to appear in a linear differential equation as far as the unknown function is just x and x prime. Okay, so we can't have any other sine of x or cosine of x or x squared or e to the x or anything like that. Now that being said, of course, these functions a1, a naught, and g, all functions of t, can be whatever you want them to be. Okay, they can be any old function, as long as they're just functions of t. So one thing you can certainly do is divide through in this differential equation, dividing out the function a1, and call the new coefficient of x p of t. The new right-hand side is q of t, and this is what we'll refer to as the normal form for a first-order linear differential equation. X prime plus p of tx equals q of t is the normal form for a first-order linear differential equation. A little bit more terminology. If the right-hand side is 0, so that the differential equation is x prime plus p of tx equals 0, we call the linear differential equation homogeneous. And in the more general case, where q of t is some function, we call the differential equation non-homogeneous. Those of you with some linear algebra experience are noticing a few familiar words. Linear, homogeneous, and non-homogeneous are going to have the same meaning here that they did in linear algebra. Okay, so the integrating factor is the key to solving first-order linear differential equations, and giving a first-order linear differential equation in that normal form, all you have to do to find the integrating factor is exponentiate the integral of the coefficient function of x. So the integrating factor mu is e to the integral of p of t dt, or e to any antiderivative of p. Of course, when you see the words any antiderivative, we usually use the simplest antiderivative, which is the one where the constant of integration is 0, and that turns out to be the case here as well. Okay, so the strategy for solving first-order linear differential equations, given that first-order linear form, which again is x prime plus p of tx equals q of t, the first thing to do is to integrate to compute this integrating factor and multiply through by the integrating factor. And it turns out, if you did your homework correctly in starting with the first-order linear normal form and found the integrating factor correctly, you always end up with a product rule on the left-hand side, just like the example we saw at the beginning of this video. So once you recognize the product rule, it's quick to integrate both sides with respect to t. Now, a couple of comments. It turns out that just like separation of variables, this procedure yields an implicit family of solutions. Unlike separation of variables, it's usually quick to identify the explicit family of solutions once you have that one parameter family. Okay, so a little bit of exploration. We'll go ahead and start with a couple of examples. Here's the first one. One parameter family of explicit solutions to the differential equation dx dt equals 3x. Now, this is a differential equation we've looked at before. It's just an exponential growth differential equation. So we know that we expect the solution to be something like x equals some constant times e to the 3t. Okay, it turns out that this differential equation is also linear, and you can see that by rewriting it in first-order linear normal form, x prime minus 3x equals 0. So we'll go ahead and compute the integrating factor. The integrating factor is the exponential of any antiderivative of the coefficient function of x. So again, in this case, that coefficient function is -3, and the integrating factor is e to the minus 3t. So go ahead and multiply through both sides of the differential equation in that first-order linear normal form by the integrating factor and integrate up both sides. You can see that you have e to the minus 3 times x prime minus 3 times e to the minus 3 times x equals 0. So that looks like the first times the derivative of the second plus the derivative of the first times the second once again. So collapse that product rule, integrate both sides. If the derivative of something is a constant, is 0, rather that something had better be a constant, and we arrive at the expected solution, again some sort of increasing exponential, just as we expected with this exponential growth type of differential equation. Okay, so this is good. Our new method works on a problem we already knew how to solve. Just for graphical sake, here are a few graphs of those increasing exponentials. Okay, so let's go ahead and have a look at another example. This one ends up being a differential equation which is neither separable nor integrable. It's not a differential equation we've looked at before. Well, actually it is, but we'll get to that in a second. Okay, so it is a first-order linear differential equation. It has the form a1 of t times x prime plus a0 of t times x equals g of t for some function g. So to have a look at this linear differential equation, we'll go ahead and start by writing it in first order linear form, dividing through by the constant or by the function that's the coefficient function of x prime, which in this case is t. So we'll divide through to ensure that we just have a 1 for the coefficient function of x prime, and we can use that coefficient function of x to compute our integrating factor. So in this case, the integrating factor is the exponential of 2 over t dt. Of course, the integral of 2 over t is 2 logs of t. We can play that hop it up trick to express e to the 2 log of t as e to the log of t squared. And of course, when you have e to the log of t squared, that's just t squared. So go ahead and multiply through our differential equation in first order linear normal form by this integrating factor t squared, and you'll recognize not only the product rule, but also the differential equation that was a motivating example for the beginning of this section. So there it is, t squared times x prime plus 2tx equals t to the fourth. And we saw how to solve this differential equation, recognizing the product rule, integrating both sides, and end up with x of t is 1/6. That should be t to the fourth plus c over t squared. A couple typos there. It should be the same solution as what we got before, 1/6 t to the fourth plus c over t squared. Okay, so we can see the behavior of that solution here, and as t gets close to 0, and another typo in this slide, it should be 1/6 t to the fourth plus c over t squared as the solution x of t. We can see that things look like x to the fourth as t gets large, and things look like 1 over x squared as t gets small, as expected. Okay, so again, I apologize for that typo. The solution x of t should be 1/6 t to the fourth plus some constant over t squared. Okay, so let's go ahead and have a look at another differential equation. So here we'll have a look at the differential equation dx dt is negative x plus 2t. So this is a differential equation that is not separable, but actually we've looked at this differential equation before. We looked at this when we had a look at slope fields. Okay, so in order to look at this differential equation as a linear differential equation, we'll go ahead and write it in that first order linear normal form. So in this case, x prime plus x is 2t, and find the integrating factor, which in this case ends up just being e to the t. Okay, so multiply through by the integrating factor, identify the product rule on the left-hand side, and integrate both sides. Here we see that when we multiply through by the integrating factor, we end up with e to the t dx dt plus e to the t x is equal to 2t e to the t. So of course the left-hand side is that product rule. The right-hand side is 2t e to the t, and there's an integral, and I've left off the differential for some unknown reason there. Sorry about that. There should be integral of 2t e to the t dt, which of course requires integration by parts, so I've left off that integration by parts as well. I'll let you go ahead and work that out on some scratch paper. But integrating both sides yields the implicit family of solutions to this differential equation, e to the tx plus 2t minus 1 e to the t equals c, for which all we have to do is multiply through by e to the minus t to go ahead and identify the solution that's at the top in the green. X of t is 2 times the quantity t minus 1 plus a constant times e to the minus t. Again, this is, as expected, an explicit family of solutions to the differential equation. So one thing we can see here is the behavior as t gets large. As t gets large, the exponential term vanishes, leaving us with just this linear polynomial, right? 2 times the quantity t minus 1. And that's actually what we saw graphically when we looked at slope fields as well. And you can see this here too, depending on the initial condition. We have different curves in the tx plane. The red one is one that goes through x equals 1 when t equals 0, and the magenta one is one that goes through -2 when t equals 0. It turns out that that magenta curve corresponds to a constant capital C equals 0, so you actually just end up with the first order polynomial 2t minus 2, or 2 times quantity t minus 1 is the solution in that case. Okay, so again, though, here the sort of cool thing is that we see something matching what we saw in our investigation of slope fields, and it comes from this part of the explicit family of solutions that goes to 0 as time goes to infinity. Later on, we'll call that a transient solution. The part that goes to 0 as time goes to infinity is the transient, and the part that remains, which in this case is 2t minus 1, is the steady state. Okay, talk a little bit about solution structure of these first order linear differential equations. So generally speaking, they can be decomposed into x sub h plus x sub p, where x sub p is what we call a particular solution. It's the solution of any solution of the non-homogeneous differential equation, and x sub h is a solution of the corresponding homogeneous differential equation. Okay, so by corresponding homogeneous, in this case, I mean x prime plus p of tx equals 0, right? So that would be the homogeneous differential equation corresponding to this differential equation. But wait, there's more. So if we have a look at thinking about this linear differential equation in so-called linear differential operator notation. So here I'm defining the linear differential operator L to be x prime plus p of tx. So Lx is x prime plus p of tx. You can sort of think of these differential operators as just a way to mix up unknown functions and their derivatives. In this particular case, we mix up an unknown function and derivative by writing x prime plus p of tx. It allows us a little shorthand to represent the differential equation. As you see up top, we can represent the differential equation just as Lx equals 0, and we can see the connection between the non-homogeneous differential equation, Lx equals q, and the corresponding homogeneous differential equation, Lx equals 0. So we can see that xp plus xh is a solution of the non-homogeneous differential equation for any xh that's the solution of the corresponding homogeneous differential equation. So this is like something that we talked about in linear algebra also, namely that you can always add an element of the null space of a matrix to any particular solution and get another solution to the non-homogeneous system of linear equations. Okay, so same thing for non-homogeneous differential equations. We can always add anything that solves a homogeneous differential equation to the non-homogeneous differential equation and get another solution for the non-homogeneous differential equation. Okay, so those of you, again, with a little bit of experience in linear algebra, this should make a lot of sense to you from that intuition of linear algebra. Okay, in this particular case, we can identify the homogeneous solution, the particular solution for our differential equation, dx dt equals negative x plus 2t, by starting with the differential operator Lx is defined by x prime plus x. We can see that the corresponding homogeneous differential equation would be something like x prime plus x equals 0. And again, that corresponding homogeneous differential equation can be written as x prime equals negative x. So of course we know how to solve this decay equation. X prime equals negative x has solution some constant times e to the minus t, and that's the solution of the corresponding homogeneous equation. And again, here we're just calling that the homogeneous solution. And again, the particular solution is the other part, right? So it turns out that 2t minus 1 is a solution of the non-homogeneous differential equation, and the general solution of this non-homogeneous differential equation is any particular solution plus the general solution to the corresponding homogeneous equation, and that should remind you of linear algebra also for those of you with some experience there. This is going to become even more important as we study second order equations, so keep this in mind for that study in chapter 2. Okay, just a quick remark about the initial value problem in the fundamental theorem of calculus. So I'll mention that similar to separable differential equations, we can use the fundamental theorem of calculus to find an implicit solution of the differential equation that satisfies the initial value, and for the integrating factor you incorporate that initial condition as well, T naught. Okay, so there'll be an opportunity to practice that in some of the homework problems. Okay, finally in this exploration bit is an exploration of a so-called Bernoulli equation. So a Bernoulli equation is an equation of the form x prime equals a of tx plus g of tx to the n. You can see that in general this is not a separable or a linear differential equation when we have n, but it turns out that there's a clever substitution that converts this Bernoulli equation to a linear equation. So here's what the clever substitution is. The substitution is try y equals x to the power 1 minus n. Okay, if y is x to the 1 minus n, we can use the chain rule to differentiate y with respect to t, and that's what we see in the first equation here. Y prime is 1 minus n times x to the minus n. That's just the power rule, and the chain rule gives us times x prime. Of course, if x prime is a of t times x plus g of t times x to the n, we can substitute that, simplify, and it turns out that this last line, 1 minus n times a of t times y plus 1 minus n times g of t, is a line that's linear in the unknown function y. Okay, so we can go ahead and solve that linear differential equation in y for the explicit solution, explicit family of solutions, and then just recover x from the original relationship y equals x to the 1 minus n. Now, one thing you could do is you could try to memorize this linear differential equation in y that's equivalent to the Bernoulli equation, but a better thing to do is just to identify the correct clever substitution and crank out the chain rule to identify a linear differential equation in y. So as an example of a Bernoulli equation, here is 1 x prime plus a times x. X prime is equal to ax plus bx cubed. So as it turns out, this differential equation is separable, but separation of variables ends up being particularly heinous, so we'll go ahead and identify this as a Bernoulli equation with n equals 3, and make that substitution y equals x to the 1 minus n power, or in this case y equals x to the minus 2, to identify a linear differential equation in y. So again, the power rule and the chain rule, or the generalized power rule, gives us that y prime is negative 2 times x to the minus 3 times x prime. Substituting the expression for x prime and simplifying, we end up with the linear differential equation y prime plus 2ay equals minus 2b. Okay, so the integrating factor is found quickly. It turns out to be the integrating factor is e to the 2at. Multiply through, recognize the chain rule, integrate both sides, and identify the explicit family of solutions y of t equals b over a plus some constant of integration times e to the minus 2at. Cool, right? So what's left is just to recover x from the relationship y equals x to the minus 2. And here it is. If y is x to the minus 2, x is 1 over the square root of y, or better written as y to the power minus 1/2. And here we have an expression for x as a function of t that we've just found by using this clever Bernoulli substitution, as well as first order linear differential equation. Okay, so that's it for part 1 of first order linear differential equations. classification, strategy, and exploration. More on applications of those differential equations in part 2. So long for now.